pleasure to introduce the second speaker this morning, Abouzaid, who will talk about CBA.
Thank you. So yeah, I'm sorry for not giving the title. So I'm going to talk about everybody's favorite subject. I'll talk about virtual fundamental chains. And of course, you know, virtual fundamental chain is well, a subject that for about 20 years only about 5 people understood, which means Kenji and his collaborators. And in recent years, there's been some further development. There's been some work of John and others. I want to. I still feel like, in some sense, well, I'm not sure it would be helpful, but for I mean, there are many symplectic people in this audience, but still, there's some kind of psychological barrier to people using this, and so I want to talk about. Sorry, it's recorded.
Yeah, even giving it as a title, there is a psychological.
That's right. That's right. And so what I want to talk about is some way of organizing it in a way that might help get over this psychological barrier. So this is joint work with Andrew Blumberg. So let me just start with what we're going to do. I'm going to have K, which is some kind of ring, and I will use my notation for mod K for some kind of derived category. And the goal in Floer theory ultimately is to construct some kind of object, CF star, associated to some auxiliary data, either a symplectic manifold or a Lagrangian. I'm going to just completely omit it with coefficients in K. I mean, let me actually just write M, pretending to just some symplectic manifold with coefficients in K. And it should be some object of this derived category. And the question is how to produce this object. And we know what data we're supposed to start with. So the starting data is always some kind of moduli spaces of holomorphic curves. And in the kind of the initial, I mean, of course, there were virtual fundamental cycles in Gromov-Witten theory, which is somehow much easier than chains. In the initial place where really chains were used was this work of Fukaya and Ono. And they basically explained how to use this to define what's called Hamiltonian Floer homology. Maybe in this audience I should say symplectic homology, because it's essentially the same thing. So Hamiltonian Floer chains. Actually, I'm going to use chains instead of cochains. I apologize. Force of habit. Hamiltonian Floer chains. Or, you know, in modern language, maybe you want to do symplectic chains. Okay? And in this case is much, 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 much easier than the case of Lagrangians, and I'm going to just focus on some formalism that's for this case here.
What are the subscripts?
What are the subscripts?
Yeah, well,
Stars. Grade, like a graded thing. It's a meaningless subscript. It's just there for decoration. Which is some kind of, you know, chain complex. And then later, so I will not talk about Lagrangians today. Okay, so in this case, one way to organize the data, so you can organize the data as follows. So first, we have some set P, okay, I'll call it P, which is, if you know about the geometry, some kind of set of critical points of a Morse function. Let me just put it like that. Of a Morse function. But the essential thing that I will use about it is that it is partially ordered. Ordered by the values of this function. Of course, again, if you know about Hamiltonian Floer theory, you realize that orbits are not actually ordered by the action. You have to pass some cover, but then you can just go upstairs and have some kind of group acting on this. And then the next thing you have is that for each a pair of elements of P which are comparable, we have some space. And I'm going to write just n bar PQ because there's no reason for me to say notation for anybody, which you should think of as some moduli space, and it's compact in Hausdorff. Okay. And then the third ingredient that we have is, of course, that we have some products. And the product is associative, which basically means you can encode the data of 2 and 3 as just saying that if you think of P as a category, you have another category, let's call it n bar, which is some kind of topological category, over P. This is the starting data of every single one. And the goal is to figure out how to extract from this data a chain complex in K-mod. Object.
You don't include the master equation as part of your starting data?
I don't want it. There's no, yeah. I mean, this is the starting data. Okay. And so I'm going to, at some point I have to, K has to enter the story. And the way K is going to enter the story right now is by, so we will associate, so I'll start by associating. To this data another category, which I will call the cochains of n bar rel boundary with coefficients in K. Oh, okay, so here I'm going to put a -1. And so how is this defined? Well, with a category which I call this, which is now enriched in, in K-mod. So the objects are as before. And the morphisms are going to be given by, well, we define the boundary of n bar PQ to be the union over all composable morphisms. Let me just, it's easier to set it like this, PR, over Q1 to Qn of the images, but I'm just going to abuse notation and not write the images, PQ1 cross n bar Qn. Okay, and if you have such a boundary, and if you have a reasonable theory of chains, you can then define the object, the morphisms of this category here. Evaluated on the pair PQ to just be, and just this is done notation, cochains again with shift by 1, n bar PQ, rel its boundary, with coefficients in K. So I claim, so right now this is just some definition of some K modules that are associated to these spaces together with this, this boundary, boundary. And then all I want to say is that the composition well, it has to, when I say it's a reasonable theory of chains, means we have to assume that the chains have somehow multiplicative. I.e., we have a map of quotient, theory of quotient. we have some math from the cochains on X, coefficients in K, tensors, cochains on Y, coefficients in K, cochains in the product.
So when you say C star minus 1, does it mean?
I shift degrees by
shifted by 1? So
Degrees
now
by
in the composition, there has to be a shift.
Yes, and it's because I'm going to use a boundary homomorphism, and that's what's going to account for that shift. But I'm going to get to it in a second. Right now, because I'm about to write what I need. I need the quotient to be multiplicative, so I need this map. And then I need a boundary homomorphism. Which needs some kind of cochains. X, I'm going to do what the topologist would do. Chain on A. I can never get my numbers right. I think this is going to be +1 here. You need the boundary homomorphism, and they need to be reasonable. And if you combine these together, and what you get, I'm going to just do a toy case where there's basically 3 of them. So if, let's say, P is less than Q is less than R, you get some map from cochain +1. Okay, I'm sorry, I might have gotten the ±1 wrong. I'm going to keep the 1 here and then see if it's okay. Oh, no, I think it's fine. Of M bar PQ, okay, tensor -1, M bar PQ. Okay, oh, QR. And then you multiply them, -2, the product. Okay, I tend to write the product like this for shorthand notation, and put QR. Okay. And then we did relative cohomology, and so this is exactly, and this is lives in the boundary, so you get something like this.
Accidentally introduced some notation in bar QR.
Yeah, M bar, I did it right here. I cheated. I said I needed to introduce a notation, and so this is, when I write this product here, I just write it like this.
That's
Okay? No?
So the sources originally chains about boundary, but I guess you just include.
Yeah, if you only have P and Q and R, then nothing else. And you have this chains here and cochains here, real boundary, but here you need real boundary. But of course I could have put real boundary everywhere. Doesn't.
So the input is not relative chain, it's just a chain.
Because these, I assumed these were closed. I mean, maybe I should put relative chains everywhere here too. Then it's clear. Here, if these are the only objects that you have, then these have no boundary, and therefore you can make this. Okay, so now I can get to something what I want, to the goal of this statement, which is just following the definition.
so in general, it's the exact sequence for a triple.
Yes. Yes. The definition. And I'm going to put here twisted because I don't want to be virtual fundamental chain on. Okay, so John really doesn't like it when I do things like this. So I was listening. He would probably say compatible system of virtual fundamental chains on all these moduli spaces. But I just want to say on this category. On the category, a bar is a functor, which is actually k-linear. From this category that we just did here to k modulus. Okay, that is my claim as to what it is that we are doing when we're doing virtual fundamental chains. Okay, so now Paul kind of, already burst the bubble because he asked, in general, this is just could talk, it's like this is just a boundary homomorphism, so it should hold for any homology theory. So really, the work is not about K being a ring, but about K being an associative ring spectrum. And mod K is the derived category, which is just category of modules, whatever they are. And the goal of this is to explain in a way that doesn't matter whether you're doing homology or K-theory or coordinatism, what it means, what it is that you're doing when you're building fundamental chains in some uniform way. So the first thing you would ask, yes.
This category, okay. So this category is bounded, right?
Yes, this kind of sorry, I forgot the boundary.
So what are the values on an
I have not
object?
defined them. I have not told you what they are. That should be part of the twisting data.
Roughly speaking?
Roughly speaking, I'll say something in a second. Roughly speaking, they are the orientation lines that we always think about. That would be the most classical situation, and I will do it, and I will say something. Okay. So the first, if I do that, the first thing you should say is what do I mean when I mean cochains in this context? And what do I mean when I do these expressions? But realize nothing that I wrote down used addition. I just used some kind of tensor product, some kind of boundary homomorphism. So it's completely reasonable that such a theory exists, and roughly speaking.
So when you said associative, you really meant non-commutative?
I did not have to be. Nowhere needed commutative.
You don't need commutative.
And it's because here, when I said that this is multiplicative, you should interpret this as there's a monoidal functor from the category of topological spaces to the category of whatever, and I don't need the fact that it's symmetric.
But that's because you're doing like a
I'm doing homology
theory, not type category, because in an infinity category you have this.
So I think what John is saying is, if you want to make sense of a notion of an algebra over a ring, it better be that the ring is commutative. Okay, and so I'm not making sense. I'm just talking about just defining some module.
Sorry, so one more question. Is it a functor to rank 1K modules then, since you're saying orientation lines?
Well, that would be the simplest case, but somehow I want to do something very general. So Simon over there in his thesis is doing something about how to do Floer theory with Q coefficients when you don't have orientations. Okay. And you can do this as long as you are willing to take the correct module. And sometimes they're infinite dimensional, which is the obvious thing to do, but actually sometimes there's finite dimensional things you can do. And they make just as much sense.
So this is also why you don't want to put the virtual dimension shift on the left regardless of change you want to.
That's right. It will have costs later. So sorry, this is minus. I saw this minus 1. Okay, so from now on, I'm not going to write C star minus 1. I'm going to write what I always would have been boundary and bar, and here I'm going to write loops K, which you can just interpret as shifting it by 1. That's all it does. And the advantage of doing loops K is that kind of you know what you mean when you say 1. I mean, there's this problem when you're not doing homotopy theory where I don't quite know what to say. Rn has symmetries, whereas the number n, whatever. Okay. So I should give some idea for what is happening here.
Yeah, that'd be useful.
Yes. So the basic case of this is Morse theory. Sorry. Next case is Morse theory. So in that case, then the work of Cohen, Jones, and Siegel implies that the assignment which sends every critical point to the chains of the sphere bundle on the negative eigenspace. So I'm sorry. F goes from M to R. P is a critical point. I'm going to put T minus P M with K coefficients. So the thing that assigns to every critical point the chains on, this is the sphere on the negative definite subspace of the Hessian.
Chains no boundaries? Sorry,
Reduced
chains.
chains. Negative definite subspace. Of Hessian. This assignment extends to what I call a twisted virtual fundamental chain. On the category where the morphisms are the moduli spaces of gradient floating vectors. M bar PQ is moduli space of gradient flow. And the key idea, of course, so the key point is that we have isomorphisms. Something like this. I take the tangent space of the moduli space. I take the direct sum of R, take the direct sum with R. And then, okay, I didn't tell you whether the gradient flow lines are down or up, so I can write whatever I want. Direct sum, this negative definite subspace of the tangent space is isomorphic to the one at Q. Okay. And so this R here is kind of amazing. I still don't know. It's some kind of amazing coincidence. This R here is exactly corresponds to the shift by 1. And so this theory, this tells you that of course, people know very well that this thing is oriented relative to these two things. Okay. But you don't have to say that it's oriented relative to these two things. You actually have this isomorphism. And the fact that you have this isomorphism here, it tells you you can work over any cohomology theory. It doesn't matter if you're integers or not, if you're a ring or not. And so once you have this, you interpret this as saying that the space M bar PQ, which let's say it's a manifold, is oriented relative this pair, T minus QM, T minus PM. And so if you have this orientation, it tells you that the cochains of M bar PQ with coefficients in K are essentially real boundary, cochain real boundary of M bar PQ. Well, I'm just going to use this isomorphism here relative to some kind of line bundle, which is some kind of sphere. I'm going to just put some kind of pluses and minuses. T minus M, direct sum T of M bar, direct sum R. Oh, that actually the R disappears because the R is eaten by this. Okay, this minus the other one on the other side, T minus QM, okay. and then tensored with K. And so already here you see that I'm using some kind of notation for homotopy theory. If we were really doing like algebra and K was a ring, I would just say take this orientation line here and tensor it with the opposite of the orientation line here, and then tensor it with K, but I don't want to keep this notation. And now there is Poincare duality, which tells you that this is isomorphic to the chains of the moduli space with coefficients, and basically this M bar disappears. sphere, T minus M minus T cubed, also T cubed K. And this Poincare duality is an equivalence. Okay? And now once you're here, you can just forget to a point. Okay? This goes to the sphere
So
on.
instead of Poincare duality, then your modular space is manifold or something.
That's right. So this is part of the reason why I'm saying, if you do Morse theory, let's say you assume that you have that you've made sure that the moduli spaces are smooth. Okay. Then here you have to say you have Poincare duality. Of course, I already assumed it because I wrote the tangent space of the moduli space is isomorphic to this, so it was already in this line here.
So you say that the chain level Poincare duality, one need a bit careful choice about the chain models.
So yeah, so this is part of why I'm writing it like this. So with this model, there is actually a canonical map this way. And I wrote
But they are
it.
chain, that is like singular chain or something? Or?
No. So, which is of course what's hiding in here. I write chains, but I don't mean chains. These are not chain complexes. Because I want to be able to use homology theories which are not ordinary homology theories, and those can never be computed by chain complexes.
So it is just a homology, just some general homology.
No, it is not a group. It's a spectrum.
I see.
Okay? So what this literally means is there is a collection of spaces, one for every integer. Okay? Really one for every representation, if we're doing some geocoding, but anyway, one for every integer. And there's another collection of spaces, one for every integer. And these are connected to each other by some maps, some kind of suspension maps. And these are connected themselves. And there's a map from this one to this one. Okay? And stably that induces a homotopy equivalence. And that is the statement of this Poincare duality is being used here.
Can you explain what it literally means when you write C star?
C star is actually the easy one. C lower star or upper star?
You can.
Okay, so can I finish this and then I'll get to it?
Sorry, that should be a TPM.
I haven't, I don't know where I am. Oh, this one should be a P.
Then you should tensor this given spectrum.
I haven't, no, and I don't want to. Here what I want is, let me write like this. From this T minus PM. Okay.
So all the work is in this Poincare duality then?
That is some way of thinking about it, yes. This is some statement which is completely abstract. You want this functor. Question is, how would you ever produce this functor from geometry? And the answer is, of course, by Poincare duality. Okay, so this is easy to understand, and this is, this map is trivial, and here this is easy to construct, and all the work is in the construction of this equivalency. Okay, T minus N and the S to the T. I guess I might have gotten something wrong, but minus P M tensor K. In K modules. And this map is just basically project to a point and then this plus and a minus and you just do that. Okay, so now, Vivek wants to know what do I mean by this guy here?
Actually, while you're at it, you can also say we can write tensor product.
Sorry, what?
Maybe you can also say what tensor product.
Well, the K is yeah, I mean smash product.
You need smash.
Of course I mean smash product, yes. Yeah. But of course, again, you can either interpret, you can write down. I think what I'm telling you is that these are the recipes that we need. Of course, we all know if you're doing chain level theories, you better have a good chain level model for Poincare duality here. One thing you don't need to invert this map, and I'll explain later what you can do to that. You don't have to invert it, but you just at least need a map that is sufficiently functorial. Okay. So again, so if we're working in spectra. I mean, anything I will say will be a lie, but anyway, the chains on space X with coefficient K will be, well, I take X, and I just basically take its suspension, and I smash this with K. What does that mean? Well, what it means is I look at, this is basically the collection of spaces X, S1, its suspension one time. I'm going to do this one. X plus, sorry. We'll add an extra base point, dot, 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 dot. You just, this collection of spaces, there's clearly a map from this one to that one. And K is, that's part of what the data that it has. It has the data of a collection of spaces, one for every integer, and then maps between them, associated to passing from one level to the next. So that's what this guy means, and you have to understand what the smash product means. This is actually kind of delicate. It's probably the hardest part of the subject. of stable homotopy theories to actually write down a good model for the smash product. Okay, so I'm not going to do that. But naively, what it is that you take the n1 and the n+1 and n1, you multiply them together, and you end up with n plus m. Now you need to make that compatible with the fact that there is more than one way to end up in n plus m. Decompose. Okay, that's why the subject is hard. The cochains.
Can you just say which model you're using?
Orthogonal spectrum. Cochains of X is, well, something very similar, some kind of basically functions from the suspension spectrum of X to K, okay? Which basically means you're going to look, the n space of this is kind of the inverse limit over all n of the maps from this one to that one, okay? But then that's at the 0th level, and the next level is the map from this one to, from this one to this one with a shift by n. It's kind of a model. So this is kind of functions.
So this is spanning your right.
Well, if X and, yes, that's right. There's that's right.
So F means the space of all maps.
Sorry, what?
F means space of all maps.
F means, yeah, so it's called as a function spectrum, but you should be thought of as the space of all, so this is a collection of spaces, one for every natural number. This is a collection of spaces. It's the space of all maps from one level to the same level, but compatible with the sequence. So it's some kind of limit. But again, in some sense, what I'm trying to explain is that there's a formalism, okay, and of course it's not clear that this is what preventing symplectic topologies from using it, but somehow, certainly, if you want to do this with k that is not the integers or q or something like that, you just need to put things in a formalism so that you can understand what you're doing. Okay, so
C0. Continuous map.
What?
Continuous map?
Continuous. This is usually just continuous map.
And there's no differentiability, right?
No differentiability. Yeah, this is just all continuous map from this space to that space. Okay, so let me just say one thing about this Poincaré duality. The map that you can, okay, let me just say something about Poincaré duality. Okay, so, to be honest, we don't construct, we don't construct the map from here to here. What we construct is a zigzag of equivalences. Okay. Okay. And the reason that that's okay in the end with this definition, okay, is that here I'm suggesting that you should take a composition. Okay? But actually, what you really end up doing is you construct a category where these are the morphisms. Then you construct another category where these are the morphisms. Then you construct another category where these are the morphisms. Okay? This one is particularly easy. Okay? This is just the most naive thing you could have done. If you had started with a topological category, in practice, each of these steps is implemented as a functor between k-linear categories. There is a k-linear category whose morphisms are the relative cochains of the moduli spaces twisted by something involving like the tangent space and these things that determine the orientation. Okay? This one, in some sense, is the easiest one, which is that basically there is a k-linear category where you just take the topological category and you take its chain and you take the chains. Okay? You take the chains and you twist them by this.
In that bottom one, when you do the non-transfer setting, do you use the dualizing sheaf or not?
This one?
Yeah.
This no, we do
The bottom
not.
circled one.
These are the exact same formulas that appear in the non-transfer setting as well.
So then the virtual fundamental cycle appears in this Poincaré duality error.
Virtual fundamental cycles is in the Poincaré duality. Yeah, that's right. It's because here the tangent space disappears to nothing. And then you don't have any tangent space to deal with. Categories. Oh, so let me just do it like this. So I'm going to give like, again, cochain minus 1, no, cochain round boundary of n bar with coefficients of k, and then some category C1 and some category C2 and blah, blah, blah. Okay? And at the very end, there's some last category that you end up with, and then you map to K modules.
But then doesn't this point where you draw the arrow go the other way? Because it's cap of the fundamental class.
So I can explain how this one goes.
Well, but it's an isomorphism, so my question only makes sense for a non-isomorphism case.
Yeah, so this, at the point set level, we constructed this way.
Real boundary is the
Yes, rel boundary here. Yes. At the point set level, we constructed this way.
So it is something like a homotopy group or something like not isomorphism.
Yes, I'm sorry. Yes,
This
this is
one
an
is
equivalence.
equivalent, yeah.
Yes, exactly. In equivalence in K modules. Okay, which means indeed it's an isomorphism on it's an isomorphism on homotopy groups. This is a collection of maps, spaces of maps from something to something else. This is just some space stabilized, and stable homotopy groups of some space are in the same stable homotopy groups of some space and maps. Okay, so then you get a functor between K and new categories, but it turns out that each of these are equivalences. And then there's an easy way of unrolling a collection of equivalences to a single functor from here to here by just taking the tensor product of bimodules. So a lot of the, people know that somehow, okay, it's really hard to write down a good chain level model for Poincare duality. It's even harder to try to invert it. Okay, but of course we never invert it. You just formally invert it, which means that when Paul asked me what are the values of these functors, well, it is something which is equivalent to this sphere. But of course it's a huge bar complex that is equivalent to this. Okay, so that's the definition. The claim is, how do you use this definition to do anything? In fact, right now, all I've said is, I assert that if you have a topological category, then the notion of twisted virtual fundamental chain that we should think about is this one. Okay? So there's two things in order to justify this, you need two things. You need one, well, you need to explain how a Kurdish structure gives rise to this. That's essentially what you need to do. So maybe I'll use some terminology here. A K-oriented Kurdish structure. To virtual fundamental chain in the setting. Okay. So what's going to happen basically is that the Kurdish structure should be oriented relative whatever it is the target of this functor should be. You should have it in mind at the beginning, just like here. Kind of I played this game where I knew where I was going to end up. So the first thing I did is I introduced the orientation line of the descending manifold in my theory when I went from ordinary cochains to cochains twisted by the tension bond. And two, I need to explain how to produce the Slur cochains from this. Because, okay, you have this thing, but what are you going to do with it? You want to somehow produce from this the data of some actual K module is going to be Fleur chains. Fleur chains. I'm so used to Fleur cochains. Okay, so I'm not going to talk about one. I mean, somehow one would be a whole other business. Let me talk about two, because it's not.
Maybe I might ask that. Then that's the case when isotropic group is 2.
Okay, so what we actually do is that we claim that this formalism works even when the isotropic group is non-trivial. Okay? So even if the isotropic group is non-trivial, for example, if K is Q, I claim that you construct this thing. Or maybe you don't construct this thing, but because you have specific applications. But if you wanted to construct this thing, you could. Okay? And my point is going to be that there are other homology theories, but not today. Maybe in a month I'll explain how.
But it doesn't work for Z, right?
It does not work for Z. I do not know how to make this work for Z.
It doesn't work for Z means that if there's isotropic, it failed to be Z-oriented, or
This map is not you cannot construct this. There's isotropy, you cannot construct this map so that it's an equivalence. And since you cannot construct this in equivalence, you cannot then invert it. Or rather, you could invert it, but you have no idea what's going on when you do that. You formally invert it because I said you realize that there's a tensor product and bimodule. You can invert anything, but it becomes meaningless. You can't control the homotopy type of what you get. Okay. So, but of course, with Q coefficients, orbifold type orientations, so you get this. Okay. So.
Can I ask one question about your basic case?
Yes.
So, does your theory of virtual chains allow you to do Morse theory with non-Morse functions?
Non-Morse or non-Morse smale.
Okay.
But of course, that would require you in this Poincaré duality step to not just say Poincaré duality, but actually to build in the Kuronishi structure on the moduli space. But yes, John can do that too with Q coefficients, with Z coefficients. Okay. Oh yes, I should. Okay, no, we're not there yet. Okay, so let me talk about one. No, let me talk about two. I'm not going to talk about one. Okay, this is just somehow not for today. So this is the part where not working over rings makes things kind of quite a bit more painful. So let me step back and remind you. So let's recall that when I started the discussion, I said we started with a partially ordered set. So we have a bar, and I said that we have this projection map to P. Okay, and this is some kind of topological category, and this is also a topological category. Okay. So you can apply the same recipe to this guy. Yes. Discrete.
What's the map?
Every moduli space goes to a point. This is a partially ordered set. This is the poset of objects, the poset of critical points. Okay. So this map induces a map in the other direction on the category of relative cochains. P. Okay? And so therefore, if I have a virtual fundamental chain, what I can do is I can just compose with that canonical map over there.
Sorry,
Yes?
I'm slightly confused here
Yes.
because it seemed like your original definition with. So when you said relative homology relative to the boundary, in the case where the boundary doesn't embed.
Yeah, you have to do it homotopically. Yeah. So you
And so what is C star DP?
I'll draw some pictures. That my goal is to do some pictures for that. I mean the toy cases. They become very complicated very quickly, but let me just say. So that leads us to the following definition. A P cellular diagram in K mod is a functor from this cochain L boundary of P and K to category K mod. And it's clear from the definition and from what I just wrote over there that if you have a virtual fundamental chain, then you have this data. Okay? All I'm trying to say is that by the time you've constructed virtual fundamental chains, you usually then forget about the moduli spaces themselves. You just say, well, I have these pluses and these minuses, and I just take these generators and I just take differentials with them. This is the same day now in the story. I'm not going to forget about the moduli spaces. So what does this category look like? So as Paul noted, since I'm doing relative homology, I'm not really doing relative homology relative image. I'm doing relative homology relative I'm kind of doing some kind of homotopical version of it. So the easiest way to think about it is we can thicken
Were you doing that before also?
Yes,
or-
the whole time.
I see.
Yeah. Which of course, any homotopy theorist would have to do that because they would say your notion better be homotopy invariant. And this is the only notion that's going to be homotopy invariant, the one where you have to kind of stick in.
If I were doing usual homology, would I have also had to do that?
Well, it depends whether the map, yes, you would have said, if you take a map of spaces, people would say, if it's a cofibration, then you can blah. Then you do relative homology and it makes sense. So if it's not a cofibration, you turn it into a cofibration and then you take relative homology. That's what most people would call homology MREL A.
I see. It is somehow in most classical cases, it's just an inclusion and therefore cofibration.
That's right. That's right. Closed inclusion, therefore.
How about if you have two boundary embeddings whose images overlap? Then each of them could be a cofibration, right?
No, that's right. So you have to somehow figure out how you're going to.
So there's more conditions that each one being a cofibration.
That's right. Yes. What you need to do is you need to thicken the whole thing so that the entire diagram becomes cofibrant. So we're going to thicken P. Okay. We're going to thicken P. So now I'm going to do some examples because this is getting a little bit crazy. And what you do is you can thicken P. The best way to the way that I know to think about this to thicken P to some kind of cubical complex. Okay, so let's do the toy case. One. So let's say that there are P consists of only two objects, P less than Q, and there's nothing to do. So I just wanted to say this. Let me keep going then. There's nothing to do, and so this chains here rel boundary. So you just get that these chains rel boundary of P with coefficients in omega k is just a copy of omega k. Okay, and now what I want to point out is that let's see what happens in Morse theory. So in Morse theory.
You mean the morphisms from P to Q are copied?
Yes. Morphisms from P to Q just consists of this concept. So in Morse theory, what you get is, as I said, copy of omega k, going to some kind of cochains of the moduli space, PQ, coefficients in omega k, which then is equivalent via some zigzag, which we don't want to understand exactly the details of the chains of the moduli space with coefficients in that sphere. That's okay. Which then we map into Hom K of a sphere. And so you get a map from here to here. Okay? And now you know exactly what you're supposed to do. That's the advantage of this situation. If you have a map from this to this, then you have a map from this object to this object, and you take the cone. The homotopy type that you want, or whatever, the Fleur chains or the Morse chains, are the cone of this map. Okay, so let's do the next case.
Like in the ordinary description of Morse theory, where is that cone?
Where is that cone?
If I was like learning Morse theory as an undergraduate, at which moment is that cone?
That cone will be telling you that your space is being described by taking the stuff below a certain critical point, then attaching exactly one handle. And that attachment map there's a map, boundary homomorphism. That boundary homomorphism is this map from this guy to this guy. That you get is the image of one in here. And the good thing, you can see the shift by one. There should always be shift by one. You might, in this theory, incorporate it like this. So now let's say that P consists of three things. Okay. So when I say that you thicken it to a cubical Morse chains, cone of this. So say that P is less than Q less than R. So then I say you have to stick in P to a cubical complex, and it's pretty clear what you're supposed to do. So let me now write it as this thickening. So here there's just a point, here there's just a point. And here, what you do is you create an interval like this, and this endpoint is labeled PQR, and this endpoint is labeled PR. Okay? And the map, so you multiply these two, this by this, and you end up here, and the other ones. So if you take the, let me just note, as you would expect, that the cochain's REL boundary of P, I'm going to write here, PR, omega K, is actually contractible. It's basically 0. It's acyclic.
So you put one vortex for each chain.
Okay, so here's what you do. For each composable sequence, I'm going to write the generalization. P less than Q1 less than Qn less than R, you get cube 0, 1. Well, you could write 0, 1 to the n, but it's really 0, 1 to the set. It is labeled by this sequence Q1, blah, 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 Qn. Okay? And if you ask me, now maybe I can, if you ask me how I should think about these interval directions, they have some kind of, they seem to have some canonical meaning in Floer theory, which means that, like this, in Floer theory, what does it mean to have a composable sequence like this? You can have some kind of like P, Q1, some kind of flow lines like this. If you try to think about gluing in Floer theory, then you need some kind of gluing parameter here. And that gluing parameter you can think as living. So this is essentially some kind of space of gluing parameters for what you want to do. Okay? And when the gluing parameter is at 1, well, okay. Usually we use gluing parameter 0, infinity, but okay. So if the gluing parameter is 1, then that basically means you are in the image of the gluing map. That means that you're a product. Image of, I'm just going to do this one, MPQ1 cross MQ1R to, we've got the bars now, PR. Okay? So this construction here, where I'm saying the way to think about this relative cochain is to do some kind of thickening by some cubes, it's actually extremely natural from the point of view of Floer theory. And actually, this construction, something very much like this is in FO cubed, as I learned, about 2 years after basically thinking of it, because they use collars at some point. I didn't realize they used collars at some point. So at some point they use collars, and these are exactly the parameters for the collars. And in fact, when I write C bar and bar, we also use collars to make it obvious that this map exists. Collars. Okay. But my point here is that the space of maps from here to here is contractible. Okay? But nonetheless, it has non-trivial.
So this uses strictly associative gluing?
That's, no, you don't need, this is the point, you don't need, if you attach collars,
Yeah.
then you have strictly associative gluing. Because the gluing takes place in the collar, where there's no gluing, where the gluing is completely
So you
formal.
will attach collars to these moduli?
I literally attach collars to all moduli spaces in sight to get rid of the, to the associativity of gluing problem. It just eliminates all the issues. Yeah. Of course, it's great. The whole point is that when I talk about Poincare duality, I did not need smoothness, which of course I didn't explain how that works out. Okay, so maybe that gives some idea for what the picture looks like.
I have a question.
Yes.
If you took your POSET
Yes.
and you add to it some fictitious arrows, completing it to a total layer. But let's say you just complete it to a total layer arbitrary.
Yes.
Does that change?
Yeah. It's non-trivial. Well, it doesn't. What does it change? I haven't said anything yet.
No, it doesn't change the whole function.
I don't know what you mean by change. You can extend the whole functor, like just trivially, to if you add extra arrows and there's no morphisms there. So you can extend it, but actually I haven't done anything yet. because all I've done is giving definitions. There's a definition of virtual chain, here's a definition of a cellular diagram, haven't done anything. Okay, now I'm going to define something.
Define the flow chart.
Yes, that's right. So, I don't like this term, but unfortunately it's the only term that seems reasonable at this stage. If you have a better term, I'm going to call it the geometric realization. But I'm not ready to define it. Well, okay. Of a cellular diagram. A diagram is obtained as follows. Okay. One, you do something kind of similar to what Vivek just said he wants to do. He wants to add more arrows. Actually, I'm going to add one more object. Let's add a terminal object. P plus the P with the terminal object. Two. So I'm going to call P cellular diagram. Okay, so let's call it function delta. Or the cell diagram delta. Let delta plus be the extension of delta, the original thing. Delta goes from the chains on P whatever, to delta to the relative cochains of P plus omega k to k modules. Okay, it's an extension which is trivial on the new object, sending the terminal object to something contracted, to 0, 0. Okay? Now finally, I want one more ingredient. Let k plus be the functor from cochain plus omega k to k mod, which sends all objects, sends the terminal object to k, and all other to 0. Okay, so these are my ingredients. I start my cellular diagram, I add a new object, okay? I extend my functors before in the stupidest possible way. I create a new functor, which actually I want to think of it as contravariant, but it has so little structure that it's hard to tell the difference. Okay, and then you define this geometric realization, which is basically the Floer chains, to be the tensor product of these two modules over this category. Okay, so this is kind of a crazy definition. And you know, the thing that would make me the happiest is if there were some simpler definition of this thing. The issue that is happening right now is that if you try to think about what you're supposed to do, the only other way I know of describing it is you're supposed to do some kind of iterative push-out construction. And you have to do some kind of, this was some kind of, when I said you take the cone, well, if you want to describe it homotopically, that's some kind of push-out. If you have 3 of them, like here, what you should do is you should cut here, you should do some push-out, okay? Then you should realize that the data of this thing means that this guy here maps into the push-out, okay? And then you should take some push-out of that too. Okay? So how to organize that? Well, you can't do something naive. You can't say I'm going to take the co-limit. Because if you take the co-limit, well, the co-limit is this guy. This is a terminal object. There's nothing to say. Okay? You can't take the limit. This is the limit. You have no information. Okay? You have to do something else. And the only thing we came up with is this thing. So now exercise. We have no. This exercise is actually doable. If P is discrete, there's no arrows. Then, if you take any delta, this geometric realization of delta is equivalent to the direct sum over all objects. Direct sum means wedge, by the way, if you over all objects in P of the value of the functor delta. Okay. And this is, in some sense, pardon?
What's the point of this?
What's the point of this definition? What?
Yeah, what's the point?
Okay. These are the Floer chains.
I mean, what's the role of this additional terminal element?
Terminal element.
Yeah.
It allows you to, I don't know what to say. It allows for this definition to be true. For this computation to hold. Okay. It's another way to think about it, and again, I don't have much to say here, is that it cancels out the appearance of this shift in here. Remember, this category has a shift omega 1. Omega k. So you better be that in the end, when you do some construction, you kind of cancel it out. It disappears from the story. And then when you do this computation, you realize that it does disappear. So this statement ends up being, so in Floer theory, this is extremely useful. This tells you something like this. Tells us that that this Floer chains are filtered. Starts filtered, and the associated graded, which is what happens when you have no error, as graded, is generated by orbits. Is free on the number of orbits. Okay, so I think at this stage I've probably run out of time. Yes. So I'll stop. But I'll say just one word, which is that somehow there's a lot more to be said. Once you've given this definition, then there's some stuff you have to check. And in some sense, the essential thing you have to check is you have to understand how to construct maps of Floer chains. Right? You give a definition. You have no idea how to compute it. Well, the only way to compute it is to be able to define maps, in particular to define maps to Morse theory. Then you can kind of compute it for Morse theory, and then you start getting the usual computations for Floer theory. Okay, I'll stop here.
Any questions?
This is Floer chains, yes. So in this case,
Change the element to chain complex, right?
this is going to be a homotopy type. So again, it's going to be some object of this category of spectra. If you want Floer homology groups, what you do is compute homotopy groups of this. That will give you the
chain is a bit confusing name.
I'm sorry. I somehow, otherwise, I wanted to, yes.
So that it contains the case when this bottommost case, so that delta P is kind of each critical summary.
Yeah, that's a good question. We did not end up writing, whatever I'm writing does not currently do that. You completely can see how to do it. What you have to do is you have to take this P here, which currently is a discrete set of orbits, and then you make it a topological space of orbits.
Sorry, you said the homotopy groups of Floer homology?
The homotopy groups of Floer homology.
Okay. So if I assume that I would be in a situation where I can define ordinary Floer homotopy groups?
Yes.
So what would be the relation between this spectrum?
Oh, no, it just has to do with the coefficients. I'm sorry. If K is HZ, then the homotopy groups will be Floer homology. If K is the sphere spectrum, then the homotopy groups are Floer homotopy. Yeah. And then that's essentially, so what we prove, we just kind of go through the construction, we prove that in Morse theory, you do this construction, and you get something whose homotopy type is the stable homotopy type of the manifold. Yes?
Is there any situation that you know where using associative grading spectrum gives you more information than the sphere spectrum would have?
Yes, which is any situation in which you don't have orientation over the sphere spectrum, but you have an orientation over that given associative spectrum. That's the whole point. The whole point is that orientation step, it's very rarely the case over the sphere spectrum. Very rarely will have orientations over the sphere spectrum.
If you can go to the sphere spectrum, then that's is that true?
Yes. But I will also point out that when you work with any sufficiently interesting symplectic manifold, there will be sphere bubbles, and then sphere spectrum is just not the right place. Okay.
But so what kind of spectrum do you imagine, like orthogonal frame spectra or something?
So there's some kind of dream world where you think about, where you handle the problem of bubbling using some kind of equivariant spectra for all groups at once, because all possible finite groups could arise. Okay? There is such a theory. Such a theory exists. But actually, the thing that seems much more useful is to just do the broad construction.
You
Do
mean
the broad
all-
construction of the moduli space.
All finite groups.
All finite
Yeah,
groups.
not-
Well, actually, in some sense, yeah, in Floer theory, all finite groups. Yeah, in gauge theory, I guess some compact groups would also appear. But I think right now that's maybe what I would say. Yes, Kenji.
So you start from the cyber weakness theory, does it reproduce monorealism?
Yeah, that's a good question. I have not tried. I've not tried to see whether this gives Manuelesco state. And I think that would be a good question for Manuelesco. No, actually, no. It's a good question for a student of Manuelesco who's coming as a postdoc next year. So yeah, I think somehow. Yeah. Okay.
Okay, so let's send Mohammed again.